All right, let's go ahead and begin. All right, I hope everybody had a good weekend, especially if you played fantasy football. I played Stafford, and so was yelling at my computer most of the time. Okay, so let's start off by reviewing the material quickly that we went over Thursday, so we make sure we remember what we were doing. So let's look at, we're going to do part of worksheet 1.2, part of 1.3, so kind of a mixture. Okay, so it says draw the partial positive and partial negative along the carbon-oxygen bond for CH2O. So if I just draw this really quick. All right, so here is the structure. Now we're looking along the carbon-oxygen bond here. So if we're looking at carbon versus oxygen, which one's electronegative? More electronegative. Oxygen. So that one gets your partial negative. So which one would get the partial positive? Carbon. This is a lowercase delta. It kind of looks like a fancy S. It's like an S with like a curl, kind of. Okay, number 2, let's draw the resonance. Now this structure actually has a lot of resonance in here. Do you see we have our charge? And do you see all of these double bonds? If you see multiple double bonds in there, there's usually a lot of resonance. So what do we want to do? How do we start this? There's not a negative in here, so there's not that shortcut. So look, where's your charge? This positive right here on the CH2. That's what we want to stabilize. So what can we move over to here to stabilize it? A double bond. Which one will we move? The closest one. You can only be one bond away. So for example, you see single bond, and then one bond away is your double bond. These are too far away to resonate right now. So the only one you can move is the closest one right there. Oh, over here? Oh, not that, this one? Yeah, it has a hidden hydrogen. Correct. So, well, then there's going to be a charge there. So I'll show you. So this is what he's saying. If we draw this, okay, these double bonds, did we do anything with those? No, so let me just redraw them. And where did this double bond move? Between the CH2. So do you see that this is now missing a bond? Okay, there is still one hidden hydrogen. So right here there's a hidden hydrogen. There's still only one. There's not magically 2 there. Okay. So what would that charge be? It's missing a bond, so it would be a plus charge. So the plus charge basically moved from here to there. Now can I stabilize this again with resonance? This one here I could just move over. I'm not going to move that one over because then I would go back to the same thing I just did. But if I keep going around, you see I can move that one right there. So let's see what happens when I do that. Okay. Did I move this double bond here at all? No, so that's still double bond CH2. And this one here, the bottom double bond, I didn't do anything with that either. But you see this one moved to the top. Do you see that? Okay, so I'm going to move that to the top. So now where is my positive charge? The left corner. Basically, whichever bond changed. So you see here, if I put a dot there, here it has a double bond, but down here it only has single bonds. So that's where your positive charge will be. Now can I move one more bond over? Right here? Usually with these on the exam, I'll say draw 3 resonance structures or draw 2 or something. So you know how many to draw, okay? So I didn't do anything with this top one. I didn't do anything with this one. Do you see the bottom double bond goes to the left? So where is my positive now? Bottom right. And then if you wanted, you can move that one over. But it just keeps going around in a circle. Do you see that? And so anytime you have a lot of double bonds like that, really close to each other, that's just screaming, let's draw a lot of arrows in resonance. Okay? So that's when you know to recognize it. If this just had one double bond right there, there would only be one other resonance structure. Okay? But since this has several bonds you can move around, right away that tells you there's going to be a lot of resonance structures. Okay, don't worry about number 3, but let's look at number 4. So there should be lone pairs on this, and I don't think yours actually shows lone pairs, does it? Okay, so there's lone pairs. Oxygen almost always has lone pairs. Actually, it always does. So my question to you is, does resonance stabilize a structure or destabilize? Stabilizes. Okay? This one here, I have a positive charge that I want to stabilize. Okay? Is there anything I can move to stabilize it? No. So let's think about what you can move. You can move a double bond, a triple bond, or a lone pair. Does this have any of those? No. What about this one? Yes, that's a lone pair. So I could move the lone pair right there to make a double bond, right? So between the left structure and the right one, which one is more stable? The right one, because you can resonate. Okay, so let's look at number 5. We're going to draw the skeletal structure, and this one, there is a typo on this one. It should be CH3, CH2, CH. There's no subscript there. Okay, what does the parentheses mean? There's a CH2 and a CH3, and what are... It's coming off, it's branching off. It's not part of the main chain. So if we look here, going across in a row is 1, 2, 3, 4 carbons. Okay, so we're trying to do skeletal, so that's when you do like up, down, up, down. So we're going to do 4 of them. 1, 2, 3, 4. So let me label 1, 2, 3, 4. So we know which carbons we're talking about. Now on these, do we ever put hydrogens on there? No. So see, carbon 1 is a CH3. So there's nothing else we need to put. CH2, CH. Now carbon 3, this, when you have parentheses like that, that means coming off of this carbon is this. Okay? So it's, how many carbons do I have? 2. So you go 1, 2. Or it could, face the other way. You could go 1, 2 if you wanted. But do you see here, coming off carbon 3, there's 1, 2 carbons. And if you look, so this carbon right here, how many lines do you see? 2. So how many more does it need? 2. So that makes it a CH2. So right there is CH2. And this one, how many lines? 1. So what is this? CH3. So that's the CH2, CH3. Okay, and then off carbon 4, what do I have coming off here? Nitrogen. So I make a bond to N. And do you know how this is actually bonded? Do you see here that there's no hydrogens coming off? Yeah, it's a triple bond. If you see CN, it's going to be a triple bond. It's C triple bond N. But do you see a carbon 4, there's no hydrogens? Okay, so there's nothing hidden there. So there's actually only 2 bonds there, and that's it. There's no hydrogens. So the other 2 come from the triple bond. And again, I know that because there's no hydrogen shown on that carbon. So those bonds have to come somewhere else. So parentheses, most of the time means a branch. Okay? So that means this, and by branch, do you see that it's like branching off of there, like coming off of that carbon. And we'll see more of these when we get into chapter 3. We're actually going to get into naming and drawing. And we'll go more into all of that. Yeah, CH2, like 2 or something. It should just be CH. All right, so then let's look at number 3 on worksheet 1.3. So let me write these down. And I'm going to actually draw this other one out so you can see it. Okay, so let's go over the trends. For an acid, do you want something more electronegative or less electronegative? More. So let's put acid trends. We want increased electronegativity. Size. Do we want a large size or a small size? Large. So we want large size. And do we want resonance or no resonance? Resonance. So pretty much this is kind of the order of how important they are. So electronegativity would be the most important thing, then size, then resonance. Really, size only comes in if you're looking at a column, and this first one's a good example. So I have HF and HI. Now, do you see that this is going down a column, right? Group 7. F is the most electronegative atom, right? But I is actually larger, okay? So if you're looking at going down a column, that's the time when size will trump electronegativity, okay? If you're looking at, going left or right, kind of a, let's say an OH versus an HF, then that's electronegativity, okay? But going down, if they're in the same column like this here, then that's where size determines the acidity. So HI is the strongest one here, and that's because of size. So again, electronegativity, that's really just comparing like group 5 to group 7. 7 is the most electronegative, so it'll always be more acidic than something in group 5. Okay, but once you're in the same column, if they're both in group 7, then you look at size. Does that make sense when to do? Okay. So then looking at here, what's the trend we're looking at? Size again. So which one is larger? SH. Looking at this one. So what's the acidic hydrogen here? Which one do we care about? OH. And then over here? Is it the CH or the OH? OH. So you always find your most electronegative atom with the hydrogen, and that's the hydrogen you're considering. Okay, so we're looking at an OH versus an OH. Does that help us at this point? Just looking at that? No, because they're both oxygen. Okay, so electronegativity doesn't help, size doesn't help, so we're looking at resonance. Okay? Which one looks like it would have the ability to resonate? The left or the right? The right. So that's more acidic. All right, let's look at number 4. Okay, it kind of says it on there, so cover up the bottom. We're going to pretend this is all you see. Okay, so we need to figure out which ones are acid, which ones are base, which one's the conjugate acid, which one's the conjugate base. So if we're assuming that it goes in this direction, okay, between these two right here, NH3 and this acid right here, this carboxylic acid, which one would be your acid? Say the first one or second one? This second one. You can also see an acid, will it lose a hydrogen or gain it? Lose a hydrogen, or an acid will lose. So you see over here, it lost the hydrogen. And then if an acid loses, then the base then will gain. So you see it went from an NH3 to an NH4, so it gained. So this is an acid. That's my base. Okay, so if this is the base, that would make this the conjugate acid. Okay, so this is the acid, so this is the conjugate base. All right, then we want to looking at both of our acids here, the conjugate and then the acid we start off with, which one do you think is stronger? So what's the hydrogen we care about here? the OH, right? And then this one here is a NH. So between those two, which one would be more acidic? The OH. And then another thing I can ask you with this, and this was also part of your lab too, is what direction will this go in? Okay? So do you see, we label this one as the most acidic, so does it make sense that's the one that will react? Okay, because it's when you say the most acidic, that is also saying the most reactive. Okay, so when something reacts and you're showing the arrow there, it goes from reactive to your product. So we'll say reactive acid, and it always makes some sort of product. So in this case, it's going from the reactive to the product, which would be going to the right. Now let's say that this one was the most acidic, okay? Then which way would it go? It would go from here to the left, okay? So it always goes away from it because that means it's reacting, okay? Because you see, these two are reacting to make this product, and that's what the arrow shows. So it always points away from the most acidic. Yeah, it has a higher electronegativity, and this one also has resonance too. But just by electronegativity alone, it already wins. Okay, and then the other thing I want to go over, and this is also in your lab, we like pH, I don't remember it's all in there, Ka, Kab, all that kind of stuff, pKa. So let's first, so your pH scale is basically a measure of how acidic something is. So we have pH, we have 0, 7, 14. So this is bound by 0 and 14. Okay, the pH scale is. It won't go below 0, and it won't go above 14. So over here from 0 to about 7, what is that considered? An acid, base? Acid. 7 to 14 on the side is a base. And then if you actually have 7, then that's neutral. So you can look at your pH. If it's below 7, it's considered acidic. If it's above 7, it's basic. And the lower it is, the more acidic. The higher it is, the more basic. Okay, so then we also have the formulas. So let's say we have a pH of 6, okay? And we want to know the concentration of H+. Okay? Where the formula, anytime you have a P in front of something, that stands for negative log. Okay? So if you come up with your formula, pH is actually, you see the P, it stands for negative log, and what is it next to? H. So pH just stands for negative log of H. Okay? And this H plus concentration, that's what we're trying to find. Okay? So our pH is 6. So let's put that in. Okay, so the first thing you're going to do is bring over the negative sign. Okay, so now we have negative 6 equals to log of H+. So that part wasn't hard. The hard part, or harder part, comes with log. How do you get rid of log? The inverse log. So that's the button on your calculator. It's usually like right above log, like a second button, and it's 10 to the x. That is your second log, or inverse log, or shift log, however it shows up on your calculator. So I'm going to bring this over. If I press that button, it gets rid of log. And pretty much over here, you get 10. Do you see how it's 10 to the x? X is that number right there. So you have 10, in this case, to the negative 6. which ends up being 1 times 10 to the negative 6. So if you're trying to find H plus, if you simplify this formula, it's really H plus equals to 10 to the minus pH. So this one is a pH of 6. So would you say that's more acidic or more basic? Which one? Acidic. Okay, it's below 7. I mean, it's not that acidic, but it's still below 7. Okay, and we see the concentration of H plus. H plus stands for what? Acid or base? Acid. So the concentration of acid is 1 times 10 to the negative 6. So let's try to find the concentration of the base, which is hydroxide. That formula, H plus times hydroxide, equals to 1 times 10 to the negative 14. Okay, so let's think about this for a minute. Let's rationalize it. So we said that this was, we'll say, slightly acidic. Okay? So which concentration do you think will be higher? The acid concentration or the base? Acid, because we have a acid. Now, if you had something that was basic, which one would be higher? The base concentration. So let's prove that, though, mathematically. Do you see that we already calculated H plus right here. So let's plug that in. 1 times 10 to the negative 6 multiplied by hydroxide. Hydroxide is just your base. 1 times 10 to the negative 14. So what do I do here? So do you see these are multiplied by each other? So if I bring this number over to isolate that, it'll divide them. It's always the opposite. So these are multiplied, then you divide. If they're added, you subtract. So hydroxide is now 1 times 10 to the negative 14 divided by 1 times 10 to the negative 6. And somebody have their calculator? 8? Okay, so which concentration is higher? It's a larger number. We have to the negative 6 and to the negative 8. Negative 6. So you see our acid concentration was higher, which is what you would have predicted. Okay, so that's how you do that. So it just tells you in your the pH, if you have a lower pH, that means it's acidic, and your acid concentration, your H plus, will be higher than your hydroxide, which is your base concentration. And that's all that stands for. So then let's look at pKa and Ka and stuff. So we need to first, Jill, have this down before I make it go away. Okay, so we need to kind of talk about what is Ka, because if you don't understand what Ka is, then these Ka, pK, and all that won't make sense. Okay, so the basic formula for Ka is product over reactant. And it raised to a coefficient, but that doesn't matter. The big thing is product over reactant. Okay, so let's think about this. Let's say I make a lot of product. Okay, let's say it's 100 to 1. Okay, so if my product is really high, I make a high concentration of that, will my Ka be large or small? It would be very large, right? Okay, so if I have a large Ka, which is usually to a positive power, so let's say 1 times 10, I don't know, to the 8th, okay? That's a large Ka. I know it's a large Ka because I have a positive exponent. And what this tells me, without even looking at this, or without seeing anything else, that was a very reactive reaction, okay? Because what did I make a lot of? What was high? Product. So if I made, isn't that what you want to make, right? You want your reactants to react to make a product. So if your Ka was large, that means your reaction was very reactive and you made a lot of product, which is what you want. Now let's say it wasn't very reactive. You put, you know, A and B together and they do like nothing. Okay, so that means you're going to have a lot of reactant. Okay, when you have a lot of reactant, that means it didn't react. Okay, so if we have like A plus B goes to C, here's your product. That's what you want. You want to make a lot of product. This is our reactant, and as the name implies, you want it to react. Okay, but if it doesn't really react, okay, like barely reacts at all, then we're going to have a lot of this left over, right? Because it did not turn into this. It stayed as A plus B. So if our reactant is really large, because it didn't really do anything, Ka will be small. So, you know, Ka might be 1 times 10 to the negative 8. I mean, I'm making up these numbers, but you can kind of see. So I know something's small when it has a negative exponent. So I can tell by Ka if something is reactive or not. So now let's look at this in terms of acids and bases. If you have a strong acid, okay, say like sulfuric acid, they use this acid all the time in horror movies to like dissolve bodies and stuff. Okay, so would we agree that this is reactive, right? Are you going to go drink a bottle of sulfuric acid? Probably not, okay? So it's very, very reactive. So do you think that Ka is going to be large or small? Large. Anytime you have a large Ka, that means it's reactive. You're making a product. If you have a small Ka, it's not very reactive. Okay, so if I have a weak acid, let's look at water, because water can kind of be either acidic or basic. So water is not very reactive, okay? It's pretty much usually considered neutral, right? So if I was looking at this, would that have a high Ka or a low Ka? A low one, because it's not very acidic. Anytime you see A, that means the reactivity of the acid. If you see Kb, it's the same thing, except now we're looking at the reactivity of the base. And the trend is the same. So if Kb is large, that means it's reactive. And if Kb is small, it's not very reactive. But remember, we're not looking at the acid, we're looking at the base. Okay? So if you have an acid, like we're looking at sulfuric acid, we said that is a very strong acid, so it should have a large Ka. If we calculated the Kb, do you think that sulfuric acid is a strong base? No, it's a very, very, very weak base, right? So the Ka would be large here, but the Kb would be small. Okay, these are always opposite of each other. Okay, so if your Ka is large, your Kb has to be small, because that pretty much means it's a strong acid, so it's a weak base. Okay, because you can't be both, not really, a acid and a base. Okay, so you're pretty much one or the other. So that's what Ka and Kb stand for. But these numbers here, like 1 times 10 to the 8th, 1 times 10 to the negative 8, nobody likes to look at those numbers. They don't mean as much to you, I guess we can say. We like to see nice, pretty numbers like 8 or 10, okay? So what they do is they convert a Ka into a pKa. So pKa, so we have P in front of it. What does P stand for? Negative log. So I'm going to take the negative log of what? Ka. And if it was Kb, I'd be taking the negative log of Kb. Now, do you see this negative sign here? That means it's going to be the opposite trend. Okay? So if my Ka is large, then my pKa will be small. Okay, so if we have, let's do this one we did over here. Let's see, Ka of 1 times 10 negative 8. So we have Ka 1 times 10, or actually let's do positive 8 to the 8th. So we plug in this number and let's find pKa. So all you need to do is put in negative log of 1 times 10 negative 8 in your calculator. Now the order you put that in, like if you put this number first or log first, it depends on your calculator. But when you do it, what do y'all get? Negative 8. Okay, do you see that this number here is a little bit easier to comprehend than 1 times 10 to the 8th? I mean, for the average person. I mean, I'm sure y'all know what 1 times 10 to the 8th stands for, but if you're just looking at something really quick and you see negative 8, it's just, I guess, prettier to look at. And that's really the only reason they do this. Now, do you see that pKa is similar to pH? Just, they both have a P in front of them. The trend is the same. So if I have a lower pH, that means I have a stronger acid. So if I have a lower pKa, I have a stronger acid again. Okay, so lower pKa equals to a stronger acid, which equals to a high Ka. So pKa and Ka are always the opposite trend because of that negative sign there. So if you have a low pKa, that means you have a really high Ka. Okay? So it's just, pKa is just another way of showing how acidic something is. The one thing that's different than pH, remember pH is bound by 0 to 14. I have a negative 8 there. So do you see it's not bound by, obviously, 0? Okay? There are no bounds to pKa, which could be good or bad. The one thing that's good about it is that, let's say I have a pKa of negative 8 versus 3. Okay? Which one's more acidic? Negative 8. But do you see that the difference there is, it looks pretty large. If I would have done it on a pH scale, I might have gotten a 0 and a 1 or something like that. Okay, so do you see the difference between the numbers is greater? And you can kind of see that like the difference in acidity is greater than what you think it is. Okay, because if you're just looking at 0 and 1, you think, oh, okay, they're about the same. But if you're comparing a negative 8 to a 3, you can see the difference in acidity looks a lot greater, which is actually what it probably is. Okay, so pKa, you see it a lot in organic chemistry, because it helps you understand the differences in the number. So for example, like if you have a negative number, you have a very strong acid. A base like sodium hydroxide, I don't know, you might have a, depending on the concentration, maybe a pKa of 40. Okay, so I have a negative 8 versus a 40. Do you see that that's a huge difference between a very strong acid and a very strong base? Okay, versus over here, you might have a 0 and a 13, which I know those are still, a pretty large difference, but it's nothing compared to negative 8 and 40. Okay, so again, pKa is used a lot to really show the differences between an acid and a base, or even different acids. Okay, there's not bound by anything, so in a way, it's more meaningful. Okay, so pKa and pH are very similar. pH is bound by 0 to 14. pKa is not. Okay, so if you start getting these ridiculously high numbers when you're doing your calculations, or something that's negative, don't freak out or anything. You're probably right, okay, because it can do that. All right, so that is pretty much all of chapter 1 there. Okay, so let's introduce chapter 2. So chapter 1, we kind of the topics would be over like the atom. So electrons, neutrons versus protons. You know, the charge of those, where are they located. Let's see, electron configurations. Be like 1s2, 2s2. Those. The shapes of the orbitals, and we'll go over that again in chapter 2. The electron diagrams, where you show the arrows going up and down. An ionic bond versus a covalent bond. Lewis-Dot structures. Formal charges on those. Dipole moment, so can you put like the partial positive, partial negative, like we did on the first question today. Resonance, so can you draw the arrows? And acid-base stuff, which would be, if I showed you two different structures, can you tell me which one's more acidic based on their structure? You know, like the HI versus HF. And then also like pH, pKa stuff. So those are the big topics in chapter 1. So chapter 2, we get a little bit more into bonding. So with bonding, we've looked at, in chapter 1, well, first of all, what bonds? Protons, neutrons, or electrons? Electrons. And we saw that they're located in the shapes. There's the S shape, which is, what does it look like? A sphere. And the P looks like a figure 8. Okay, and that's kind of where they're located. And then from there, we kind of looked at Lewis-Dot structures, where you can look at the valence electrons and connect lines and dots. So chapter 2 goes a little bit more advanced, and you start off with what's called the molecular orbital theory. What they found mathematically, so this here is a picture of a p orbital. Okay, so if they graph the most likely position of a p orbital or a p electron, this is what they found. So if you look here, this red line here is the nucleus. Okay, so do you see that you're looking at like the maximum area here? Is that maximum area, is it over the red line? No, so it's not found in the nucleus. And then you see there's one over here and then one over here. Okay, those are just magnitudes. It doesn't actually stand for a proton and electron. That's just showing that it's going up versus down. Okay, so so this is mathematically, do you see this looks like a wave? Okay, and if we make a three-dimensional picture of that, it's our p orbital. Okay, so this is kind of like a two-dimensional graph, and then so three-dimensional is the actual p orbital we're familiar with. The point of me showing you this is that, do you see that it's like a wave? Okay, so it has properties of a wave, like mathematically it does. So what happens here is that whenever you overlap orbitals, so overlap the shapes, because that's what a bond really is. You're overlapping the shapes because those are where the electrons are found. Okay? And when you do that, they're going to combine like waves. So there's two ways that waves can combine. There's I can't think of the words right now. Constructive and destructive. Okay, so if I have, let's say this wave, here, and I want to combine it with this wave here. So I want to add these waves together. Now, do you see that when this one goes up, that one goes up? And when this one goes down, this one goes down. So when I add these two together, I'm going to make one like giant wave. So do you think that would have been constructive or destructive? Constructive. So basically, waves could add together to basically double in size. They like literally add. And then the other way Okay, do you see these are opposite of each other now? So when one goes down, the other goes up. And one's down, the other one's up. So kind of think of these as magnitudes. So if I go back to this one. So let's say this magnitude was a +1. That would make this one a +1 also, right? If they're the same. So that, and then this one would be a -1 because it's going down. And this one a -1. So when I add these, I add a +1 to a +1 would make a +2. And a -1 and a -1 would make a -2. Now if we do the same thing here, let's put our signs for the magnitude. That would make this magnitude a +1 and this one a -1. And if we go to the bottom, this one would be a -1 and then a +1. So when we add these, if we add -1 and +1, what do we get? 0. And then again, -1 and +1, 0. So whenever you add these together, you get nothing. They cancel each other out. So this one is destructive. So when that comes to bonding, because mathematically they're like a wave when we're looking at these shapes, so either the shapes are going to bond or they're not going to bond. Okay, and we have to statistically look at both of those. And this, when we start doing these, it'll make, I think, a little more sense. So that is sort of the theory behind this whole thing. So let's actually look at orbitals instead of waves. So the first type of bond, because we want to bond things together to make new structures. So one type of bond you can have is called a sigma bond. And the sign for that is this. So a sigma bond. A sigma bond means you're going to overlap orbitals in one area. Okay, so let me draw that to show you what in the world I'm talking about. So let's look at the s orbital. Let's say I have an s, and I want to bond that with an s. Now, one thing you have to do to be able to bond, the shapes have to be similar, okay? So do you see that these shapes are the same? So can I overlap this one with that one? Yes. And do you see if I brought this one on top of it, it only overlaps one time, okay? So when I do this, so let's say this was looking at magnitudes. This isn't signs, not protons or electrons. But let's say this was like our positive magnitude, and this was our positive magnitude. So when we combine them constructively, we would get a giant one, like a +2. So would this be constructive or destructive? Constructive. And in organic chemistry, we call that bonding. Okay, but what if we had a s electron that had a magnitude of +1 and a magnitude of -1? Would those bond? No. Kind of think about the destructive interference. So it does nothing, so you just kind of redraw them. Meaning nothing happens. They won't interact. So this is your destructive, and we call this anti-bonding, which means it doesn't bond. It doesn't do anything. So that's one type of sigma bond, is you overlap a s orbital on top of another s orbital. So when we have like Lewis dot structures, like, I don't know, NH3, let me just draw one of the lines here. This here, we draw it as a line, but it's really orbitals overlapping with each other. You know, maybe an S with an S. And so even though we don't draw the shapes there overlapping, that's actually what's going on. So that's what this is showing. So let's look at, there's another way we can get a sigma. It's with an S and a P. But I need the P to look kind of similar to that. So the P needs to face it like this. So do you see that this could overlap with that one lobe right there? This with this. It won't overlap with both of them, right? Just one of them. Okay, so let's do our amplitudes again. So this is a positive one. I want constructive interference. So I want them to overlap. So that means I want this lobe to be a +1, and that would make the other one a -1. So I'm going to overlap these two right here, and so that would make this one like twice as large. And then this lobe over here, did this one change? No, because we're only overlapping in one area, so this one's going to stay about the same size. So now this one's kind of like a +2 magnitude, and that's a -1. And was that constructive or destructive? Constructive bonding. So if I was doing it destructively, so I draw the same thing. I have my S, my P, and let's say I tell you the magnitude of this one is a +1. So what would the magnitude of this lobe right here be? -1. So would anything happen there? No, so just draw nothing happening, so you just draw them again. And we call this what? Destructive antibonding. And there's one other type of sigma bond. So we have an S with an S, an S with a P, and the other way we can do this is with a P and a P. But again, the sigma bond, the definition of this is that it can only overlap in one area. So my P orbitals need to look like this. So I'm not going to have them overlap all the way over, but just overlap in one of the lobes. So I'm going to join this lobe with that one. Okay, so if this lobe over here is a +1, that would make this one a -1. So I want these two to overlap. I want constructive bonding interference. So this lobe would have to be a -1 +1. So if I draw that, these two will be large when they join, and then I would have two little small ones out there. So these two join together to make a large one, and these two do nothing, so they stay small. So if I don't want them to overlap, then I would make this lobe, let's say, a +1, and that would make this one a -1, and then nothing would happen. Again, just drawing it over. Okay, so this, what we're going over right here is the understanding. This is sort of the defining what these are. So what we're going to do with this, so these are all of the ways you can make sigma bonds. Okay, so I could ask you about this. I could say, list a lot of different interactions and say which one is a constructive sigma bond. Okay, but what ultimately what we'll have is a structure, I don't know, maybe like this. And I can have you, I can ask how many sigma bonds are in this structure. Okay, so you have to look at this and know there's 4 or 5 or however many. And we haven't gotten to that yet, so don't worry, you don't know how to do that yet. But that is our goal. Okay, so this, if I say sigma bond, now you know what it means. It means I'm either overlapping an S with an S with a P, or a P and a P, just in one lobe. Okay? So let's take a break, and we'll look at, when we come back, what is a pi bond. right, let's start back up. Does somebody have the attendance? Is the attendance back there? Can you just pass it back around for the second time? Okay, so your first exam is next Monday. I know. And we will have a review for that. Let's do it Thursday during the office hours, so Thursday 1 to 2. So right before this class. So let's just not do it then. When do y'all have trig? And Tuesday, Wednesday, Thursday? I guess let's do it. We'll see it. We'll start at the end of class on Thursday, like maybe the last 30 minutes, and then we'll go 30 minutes over. If you can't stay, that's fine. I'm going to have the vodcast extended. Okay, so you'll be able to see the whole thing. So if you need to leave, you have an appointment, whatever the reason, just you can leave. It doesn't matter. It's not going to hurt my feelings. Okay, and that'll be vodcast sent out so you can see it. So I'll extend that out that day. Okay, so the review will be, I guess, from about 3:30 to 4:30. Okay. All right, so let's pick up where we left off. Okay, so these are all of our sigma bonds. They only overlap 2 lobes, so 2 areas. So now let's look at what's called a pi bond. So pi bonds overlap in 2 areas. Okay, so if we look at an s orbital, just a circle on our paper, does it look like it has 2 different areas that you can overlap? No, there's only one possible place. So with a sigma bond, you cannot have s electrons. It's not possible. But we can have p electrons, right? And how these are going to look, one way would be like this, straight up and down. So do you see if I bring those over, I can overlap this with this and that with that. Okay? So that would be a pi bond. So that's a positive magnitude. Then the magnitude of this lobe would be a positive, and this one would be a negative. So when I bond these together, what this will kind of look like, this is how they usually show it, is like this. And then they show lines going between them. Why they do it like that, I don't know. But this is how they've always represented it. So it's overlapping at the top and overlapping at the bottom. And I think they do this so you can really see that it's 2 areas there. So this would be the bonding. Constructive. So if I was doing the anti-bonding, and let's say I gave you the magnitude of this lobe is +1, so the magnitude of this lobe would be a minus, and if that's a minus, that'd be a plus. And so just like you did before, if you have the anti-bonding, they're not going to do anything. So you just redraw that with no lines in between. Nothing happens. Now, do you remember we have how many P shapes? 3. So if I'm drawing these, this is my x and y plane. Okay, so I can have a P orbital along the x. I have a P orbital along the y. So then the z is the 3-dimensional one, which is coming out at you. So it's kind of like here. That one's going out of behind the paper, and this one's supposed to be coming like towards you. Okay, so that's your Z. Okay, so we looked at X. We combined a X orbital. We come back somewhere. Over here. So do you see this is when we combine an S with a P? This one would be the X because it's just straight line. So we already used one type of P. This one would be which one? The Y. It's like a PY with a PY. So what do we have left? The Z. So this looks almost like identical, except I guess you kind of draw it diagonal, sort of. But if I combine these, so that's a +1, +1, -1, -1. Do you see that it would look exactly like this one, except just tilted a little bit? That's about it. So instead of going straight up and down, it's going to be a little bit on its side. And that's the only difference between those two. And then you can do the anti-bonding, which would be the same thing, except not bonded. Okay, so those are basically the definitions of those. So the only way I will ask these questions on the exam, I could give you, instead of usually a plus or a minus, I usually kind of do something like this. So do you see, if you have a +1, you want a +1. So you want them to be the same, right? If they're going to bond. So I can ask, out of these orbitals, which one is a bonding p orbital, let's say. So what's easier to do on the computer is colors. And so you could have this with that. So you see the light with the light. That's like a positive and a positive. And then the dark would be different. Okay. So would that be a P? No, that's a S. What if I had here and here? That's a S, yeah, anti. Let's see if we had here. Here. That's a P, right? That's anti. So that doesn't work. Then I'll just do this last one, look good. And then that would be the P bonding. So basically like this. Can you tell by the pictures of the orbitals that that would be an S versus a P? And will it be bonding or anti-bonding? Okay, so that's what I can ask from this data I just gave you. Okay, so now let's actually apply this. So in organic chemistry, we have single, double, and triple bonds. Okay? Every type of bond, it doesn't matter if you're looking at a double, single, or triple, has a sigma bond. So if I put on here a single bond, double, triple. And I'm going to put sigma, pi. So what did I just said? Everything has a sigma. So I can put 1, 1, 1. And only one sigma bond. Or a sigma means, it's going to be one of the ones where they overlap in one area. Okay, now let's look at this. Now I have a single bond. So how many bonds do I have? 1, right? Do you see that I've already used the 1 up? So how many pi bonds do you think I have? 0. Now what about the double bond? I have 1 sigma, because that's a given. Everything has 1. So then do I have pi bonds? I'll have 1 to equal to 2. And then a triple bond, I'll have a sigma, and then how many pi? 2. And this is always holds true. So if I'm looking at a structure, okay, so let's label, actually let me show my hydrogen bonds. Okay, so let's label all of our bonds as, sigma, sigma pi, depending on what it is. Okay, so if we look right here, carbon, hydrogen, how many bonds do we have? Just right here. Just looking at that one bond. So what type of bond is that? Sigma. Because a single bond is only a sigma. So let's look at this. Is that a single, double, or triple? Single, so that would be a sigma. Here I have a double bond, right? So what would that be? What combination? Sigma pi. This CH bond is sigma. What about between carbon and carbon? Sigma. What about both of these carbon hydrogens? Sigma. And between here, carbon, carbon? Sigma. And then between carbon, nitrogen? Sigma pi pi. It's like we're in a sorority or fraternity or something. Okay, so that doesn't make sense how to label those. So you could tell this is a sigma bond, and this is an overlap of orbitals in one area. It could be an S and S, an S and a P, or a P and a P, but we know it only overlaps in one area. Versus here, we have a sigma bond, which makes up one of these bonds. So that would be an overlap in one area. But we also have a pi bond, which overlaps in two areas. So you can see how they're overlapping to create those bonds. So that's something else I could ask on the exam. I could say, label your sigma and pi bonds. So you would do this, for example. Okay, so yeah. Uh-huh. Everything has one sigma bond by definition, because you don't have enough p orbitals to be able to make to go to the sigma or to the pi. So you don't have enough p orbitals to make pi bonds. So you always they'll always combine to make a sigma, and it basically, again, you saw there's only like two ways to make the p or the pi bond, so it's less. Anyway, so long story short, whenever you combine them, and that's what I'm about to show you, that by the combination you'll never have enough to make more pi orbitals, because there's not enough orbitals to do that. So if we have, for example, there's what's called orbital diagrams. Now I'm not going to go too in depth into these, because you could have a whole class just on this. But let's look at two hydrogen atoms. We want to combine these. Okay, so basically what this will tell you is, will these combine? Now, if we were doing the electron configuration of these, hydrogen would be what? 1s. For both of them, they're both hydrogen. And if I'm putting my arrows on there, how many lines for S? 1s1. And how many electrons, how many arrows do I show? 1 for each of these. Okay, so do you remember that we can combine, so we have these s orbitals, and what do those look like? Spheres. So we have these spheres that we can combine, and we can combine them constructively, which is bonding, or destructively, which is anti-bonding. Okay? Now, if you do it constructively, that means you lower the energy and they bond. So if something's going to bond, it lowers the energy. So how you combine these, we want to bond them down here in low energy to make a bond. So this is your bonding. So when we combine these, I'll have an S, if you want, or your circle, bonded with a S circle. And so would that be a sigma or a pi? sigma bond. Okay? And how many electrons did I just combine there? 2. So remember when we were doing the orbital diagrams there, the electron diagrams, I mean, and we would have, if we had 3 lines, and let's say we had 4 electrons, where we would fill them up 1, 2, 3, 4. The same thing. This is just one giant line. So I have 2 electrons, so I'm going to go 1 up, 1 down. Okay? But what's the other way I can always combine them? The destructive, right? Anti-bonding. Not that that's ideal, but they can. So that if bonding is lower energy, the anti-bonding would be higher energy also. Okay, have we used all of the arrows here? Well, there's one arrow there, one arrow there. So is there any left to go up here? No. So do you see that both of our electrons stayed in the bonding area? Is bonding good or bad? Good. So this is a good compound. It wants to combine. So hydrogen wants to combine with hydrogen. And that's why it's a diatomic. So with these here, you can do the analysis with these large structures. And what you do is you look at each atom. You say, okay, well, carbon, I have in the valence electrons, I have S electrons and I have P. So you have to combine those with the sigma and with the pi to come with a combination. And so you'll always end up with more sigma than you will with pi. So it's really just how they combine. That's how they end up coming out like that. So this is how you would do an orbital diagram for hydrogen. Now let's look at helium. These are the most simple ones. Helium is 1s2. So I draw my lines. How many arrows would I have for each one of those? 2 for each. So let's do this one just like we did hydrogen. So the first thing we're going to look at is bonding. So is that lower or higher energy? Lower. And then if I go ahead and draw my anti-bonding, it will be higher. Now when I combine them here, I'm going to combine an S with an S. So what type of bond is that? Sigma. And then how many electrons do I have total? How many lines or arrows? 4 total. How many can I put on one line? 2. So I have 1, 2. So where do the other 2 go? Anti-bonding. Do we like anti-bonding? No. So helium does not exist as a diatomic. You will not see helium bonded to another helium because it's not favorable, because you have to go into the anti-bonding stage there for your valence electrons. So hydrogen, because your valence electrons, you do not have anything in the anti-bonding, it likes to bond together. Hydrogen and hydrogen can bond together, but helium cannot. All right, but they get really advanced basically from there. Anytime you combine more of them, then you get into your P's. Yeah, so whenever you start getting P's in there, you can see that that's when you're going to start having your pi bonds in there. So like oxygen to oxygen. I mean, if we just do the valence electrons for oxygen, so we have oxygen, 2s2, 2p4. You had another oxygen. Okay, but do you see here, now we have S's and we have P's, right? So we're going to get some sigma bonds in there, we're going to get some pi bonds in there. So if we look at oxygen, oxygen bonded to oxygen. 1, 2, 3, 4, 5, 6, 8. Looks like this. So do you see here, if we're labeling this, what's a triple bond? Sigma pi pi, right? Okay? And whenever you combine all of these together and do an orbital diagram, you'll see that you'll come up with, in your valence electrons, your bonding electrons, you'll have a sigma in there, and you'll have 2 pi's. Yeah, that's how, whenever you start combining these, so sigma is always a lower energy than a pi, so it's going to combine as a sigma first, and then it starts combining as pi's. So this will always combine as a sigma pi pi, always. And it, yes. Okay, so that's how it works out. And they derive this sigma pi pi, sigma from these orbital diagrams. Okay, once you start actually making these for every single compound, you'll actually see the sigma, the pi's, and everything come out of there. All right, but at the very most, you'll just have to do maybe a hydrogen or a helium. Okay. So let's get into hybridization. Okay, so you can see that there's Lewis dot structures, but that doesn't tell you the whole picture because we're just looking at dots and we can make lines. When you look at molecular orbital theory, you see that it's not just dots combining, you're actually combining shapes. Okay, so these shapes combine to make bonds. So it's just sort of another step. Well then, valence bond theory here says the best way, or the way that you're going to overlap something, something's going to bond, is actually by hybridizing orbitals. So let's see what in the world they're talking about there. So let's look at SP as our first one, okay? A good example of this is beryllium with 2 hydrogens. Okay, so if I make the Lewis dot structure, it's beryllium, literally, 2 hydrogens like that. Okay, so our central atom is beryllium. What is the electron configuration for beryllium? 1s2? 2s2? So the valence electrons, let me just put the valence, would be 2s2. And then for hydrogen, we have 1s2. Or, sorry, 1s1. We have 2 of them. And if we put our arrows on there, we have this 2s2, so we'd have 2 arrows, one going up, one going down, and our hydrogens have 1 each. Okay? Now, how this theory, basically how it's stated, is you want to maximize your unpaired arrows. So the stronger bond means you're going to overlap an unpaired arrow with an unpaired arrow. Now, as shown, does beryllium have any unpaired arrows? No, they're both paired, so they're not going to combine very strong to the hydrogen. So what you do is you hybridize. So on the second level, there's also P's. We're not using them right now, but they're there. Okay, and then if I had a P, how many lines do I draw? 3. Now I know your valence electrons are not in there, but they still exist. Okay, how many unpaired arrows do I need? So looking down here, how many do I have for hydrogen? Total, 2. So I want to make 2 unpaired arrows. How do I get unpaired arrows? If I want 2 unpaired arrows, how many lines do I need? 2. Okay, so do you see I can get a line right here? And then I can combine that line there. Okay, so that's what hybridization means. We're going to combine orbitals now. Do you see I use one line from the S? and 1 line from a P. Okay? And then how many total lines do I have? 2. So I'm going to hybridize them. I'm going to have 2 hybridized lines, and now they're called SPs. And then how many left over? How many did I not use here? 2 P's, right? And these are just regular P's. Now my arrows I have here, I hybridize this into this new orbital. Okay? Now my two arrows can now fit right here. 1, 2. Okay, now do you see that I have 2 unpaired arrows, and those can overlap with my 2 unpaired arrows? Okay, so this is the ideal situation. And to do that, I had to combine an S with a P. So anytime you have to do that, that's called a SP hybridization. Now I'm going to show you a shortcut. I'm just showing you where this is derived from. But this is a SP hybridization because to get the maximum amount of unpaired arrows, I had to combine an S with a P. Okay, so let's do SP2. So a good example of SP2 would be BH3. So I'm telling you right now it's going to be SP2. So what am I going to combine before I even look at this? 1 S and 2 P's. Hydrogen, do you see I have 3 of those? So I'm just going to put 3 H's. This is 1S1. So there's going to be 3 unpaired arrows. You see there's going to be 3 of these. Now, what is the electron configuration for boron? Just the outer shell. 2s2? 2p1? So I have my S, my P's. Okay, so my S, I'm going to have 1 arrow up, 1 arrow down. And for my P, I'm going to have 1 arrow up. Okay, now, how many unpaired total electrons do I have for hydrogen, my outer electrons? 1, but there's how many of them? 3. So there's 3 total unpaired electrons. I can draw 3 if you want. Okay, so there's 3 of them because there's 3 hydrogens. So how many, if I want to bond boron with 3 hydrogens, then how many unpaired arrows do I need on boron? 3 also, okay? So I have 3 hydrogens with unpaired arrows, so I need 3 unpaired arrows here, ideally. But how many unpaired do I have? Just the 1 right there, so that's not good. I want 3 unpaired arrows, so how many lines do I need? 3. So you always start at the end, you go 1, 2, 3. So what did I combine here? I have 1 S and 2 P's. So now I have 3 lines that are now called SP2, because 1 S, 2 P's. So think of this as you have ingredients to a cake. Okay, you have flour and 2 eggs. I don't know. All right, I have them separate, but as soon as I put them in the bowl and I mix them together, now it's not just flour and eggs separately, it's combined, right? And let's say I make 3 cookies out of that, because for whatever reason, that's all the ingredients you need, okay? So now my cookie is called a flour-egg combo, okay, which is kind of here. So I mix these in a bowl, these 3 here, and combine them. So now these 3 orbitals are all called SP2, because I plopped them all on the pan side by side. How many leftover P's do I have? 1. So now I have my unpaired arrow. I have 3, and I can unpair them like this. So this is called a SP2. So let's go to the last one, which is SP3, like CH4. So I have my 4 hydrogens. I'm just going to draw them really quick like that. 1 unpaired arrow. Carbon, 2s2, 2p2. Now, looking at the name of this, sp3, what am I combining? NS and 3Ps. Okay, so I have 4 unpaired arrows from the hydrogens, and I want to combine that with 1 carbon. So how many unpaired arrows does carbon need to have? 4. Okay, and it only has 2, so I need to combine 1, 2, 3, 4. And so that would be 1 S and 3 of my Ps. Do I have any leftover Ps? No. And so now, once I hybridize those, I can maximize my bonding. It makes the bonding stronger. Has more electron density in there because I don't just have an S, I now have an S-P combination there. All right, so I keep bringing up this unpaired p orbital. These, anytime you have your hybridization, these are your sigma bonds. So if something's labeled as sp2 or sp3, that's a sigma. And notice always, do you see here I have 1 S, 2 Ps? That's a total of how many? 3, right? I have a 1 S, 2 Ps, so that's 3. So I have 3 sigma bonds in that structure. And so this one, how many would I have? 4. Now, if you have a P and you actually have electrons in it, there's no electrons in there, so it's not doing anything right now except staying there. But if I had electrons in it, anytime you have the P, that's your pi bonds. So for sp2, do you say I have 1 leftover P? Think of P as in pi. Then I have 1 pi bond. So out of your single, double, and triple, which one has 1 pi? Double bond. So anytime something is labeled sp2, it could possibly be a double bond. What about sp3? Do I have any leftover Ps? No, I used them all. So this is only all single bonds. I'll make this into a chart here in a second. And then the sp, you say I have 2 leftover Ps. So it's 2 pi. So that one is your triple. So our new chart, or let me just add to the one we had before. Here it is. So I have on here single, double, triple, sigma pi. So one thing you can add on to this chart, a single bond has to be, if it's all single bonds, sp3. A double bond can only be what? sp2. And a triple bond is always sp. And this holds true pretty well for organic chemistry. So let me show you a structure, and we're going to label things as sp2 and sp3, sp, all that. And you don't have to go back through and derive them like we just did with the arrows, okay? There's an easier way. Let's just do CH4, for example. I know we did this example, but let's just, without deriving it, just by looking at it. All you have to do here is you tell me how many either atoms or lone pairs are on the central atom. So carbons are central atom. Is there any lone pairs? No, 0. How many atoms? Not bonds, but atoms is it connected to? 4. Okay? So I have sp, sp2, sp3. Now if I add how many letters here, how many do I have? 2 letters. This one has 3 letters. This one has 4. What number does this match up with? sp3, so this is sp3 hybridized. So that tells me, remember sp3 had 4 sigma bonds. It will always correspond to the number right here. So this one will always have 4, that one will always have 3, that one will always have 2. So let's label these really quick. Carbon to hydrogen is a sigma pi, just sigma, right? So sigma, 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 sigma coming off of there. How many total? 4. And these bonds right here are actually hybridized bonds. All 4 of those are sp3. So let's look at, let's do a bigger one. Okay, hydrogens never hybridize because they're always like branching off. Do you see they're always coming off a carbon? Okay, so those don't ever hybridize. So if we're looking at the central atoms here, which would be carbon, 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 carbon. Now let's look at each carbon individually. Okay? So looking at this carbon right here, are there any lone pairs? No. How many atoms is it bonded to? Again, not bonds, but atoms. You see, yeah, hydrogen, hydrogen, carbon. Do you see that? So what does that correspond to? sp2. And we also said in our chart on the other page somewhere that sp3 means all single bonds. So I'm going to put single. sp2 corresponds with double bond. And sp corresponds to a triple bond. So we can also check it that way too. Do you see there's a double bond on there? So right away, sp2. So let's look at this carbon right here. Do you see a double bond? So right away I'm going to predict sp2. But let's look. How many atoms or lone pairs is it connected to? 3. So it is a sp2. What about this carbon? It's a sp because it has a triple bond. And you can see that it's bonded to carbon, carbon. And then what about this carbon right here? sp. So pretty much when you do hybridization, you're doing it with all your non-hydrogens. If you're looking at the quote-unquote hybridization of hydrogen, it doesn't hybridize. But what's the orbital involved with hydrogen? If you're looking at the electron configuration, it's 1s1, right? So what orbital is there? S. So if you want, all of your hydrogens are S. So there is one on the lab that had, something like this. I think it was, if it's not this exactly, it's pretty close. And one points at this bond right there and asks for the overlap. Okay? So do you see we're looking between hydrogen and carbon? Okay, so when they're looking at the overlap, they're usually looking at the hybridization there. So does hydrogen hybridize? No. What do you put for hydrogen? S. And then carbon, what's the hybridization of that carbon? There's a double bond, so it's sp2. So the answer for that one is an S to an sp2. Now let's look at this one because it also pointed at that bond. So that carbon is what? sp2. Oxygen is sp3. You can look at it two ways. First of all, do you see a double bond on, like, coming off oxygen? Do you see a triple bond? Do you see only single bonds? Yes, that's sp3. And then you can also count atom, atom, so 2 atoms, 2 lone pairs, which is 4, which corresponds to sp3. So either way, however you like doing it. Okay, so basically, really quick summarization of what this means. So that's the quick way to do how we just did it. sp, sp2, sp3. Now, the reason I showed you how to derive it before, just so you have some idea what you're talking about when you say something's sp3, okay? So if you have something that's sp3, you can usually just look at it and see it. But what this means, to maximize the bonding, to make the strongest bond possible, you had to combine an s orbital with 3 p orbitals. Those shapes, that we made, we combined them, mixed them together, and created a new orbital called an sp3. And that's what that stands for. And then if you have an sp2, to maximize the bonding, to make the strongest bond there, you had to combine one s with 2 P's. And the same for sp. You just combine an S with a P. Okay, so really quick here, this carbon, for example, do you see that's sp hybridized, right? So how many total sigma bonds? You just count the letters. 2 sigma bonds. So this says we should have 2 sigma bonds coming off that carbon. So let's look here. Carbon on this side here, what's this? A sigma, right? And coming over here, I have a triple bond. A triple bond is what? Sigma, pi, pi. So do you see I have a sigma, sigma, which is my 2 sigma bonds as predicted. And the other 2 left over there are my pi bonds. So a triple bond, again, is made up of a sigma and a pi pi. And specifically, that sigma is called a sp sigma, combining the s and the p orbitals. So hopefully that kind of all comes together. This is probably the most abstract organic chemistry gets, with the s's and the p's and overlapping them and making bonds. But if you can follow the actual examples we did, like labeling if something's sp2, sp3, or looking at pictures like this, and if you can tell me if something's going to be a pi versus a sigma, that like those type of examples, that's what you need for this part of chapter 2. And we'll work through some more problems tomorrow that goes over this stuff to make sure you get it down. Okay? And that's it for today.